Okay, cool. We can start. So, hi everyone, good morning. Um, yeah, so this is the last class. Thank you for sticking until the end. And yeah, as you know, we have a final on Friday at the same time, so 8 a.m. here. It'll be 2 hours and 50 minutes according to the final exam matrix. So yeah, it will be 2 hours and 50 minutes. So it will start at 8 and it will end at 10:50. And the length will be about 1.5 times the previous exams. So because the previous exams are 20 marks and this one is 30. So that would be 1.5 times. And if you look at the previous exams, there were 5 questions each. So 5 times 1.5 is 7.5. So it will be between 7 and 8 questions, maybe 7 and one short one or something. So yeah, and it will cover everything. So the story will be the same as every other exam we've had. You can have one cheat sheet front and back, and the page of balance will be at the back. So it'll just be the same page that we had for the previous exam. And yeah, that's pretty much it. So I don't have any lecture prepared for today, so you can just ask any questions if you want to go over any of the previous topics or anything else. Any questions about the exam? I haven't finished writing it, so I cannot tell you exactly what's on it, but it will be like 1/3, 1/3, 1/3-ish. But like the first exam, the second exam, and then everything after the second exam.
What's the level of focus going to be on stuff after exam two?
About 1/3.
What there, okay. This is even.
And I guess now, like previously in the previous exams, the topics were more localized, but in the final exam, the topics may cross different, the questions may be related to 2 topics. Because now we have all the topics.
Is it gonna be similar to the exams? So we have like no MCQs, no just 7 like 7 big questions.
It will be produced to the previous exam that I have written, so it'll be similar to exam 1 and 2.
Well, will you release the answers for the last few homeworks?
Oh, I have released them.
Oh, you did? Okay.
Yeah, sorry about that. I did it over the break, so you
Oh.
you may have missed it, but yeah. So everything is there. The answers to all the homeworks are on Canvas, and the answers to the previous exam 2, I think, are also there. I posted the practice final questions, but I don't have an answer key for those, so I could not post them.
Would you say doing all the homeworks all over again would suffice?
What does suffice me?
Suffice as in, would it be enough to cover whatever's covered on the final, or would we need anything from like, let's say exam 1 or 2?
I think doing the homework, or you don't necessarily have to do them again, just reviewing the questions then would be a good way. Yeah, definitely that would help. I think there's some stuff that is not in the homework, like for example, graph algorithms. We didn't have a homework on that, but graph algorithms, there's really nothing new there. Like there's just basically matrix algorithms. So if you're familiar with matrix algorithms, you should be familiar with graph algorithms. Yeah, and there will be no MPI.
You go over graphs.
Yeah. Yeah, so we are going to go over graphs. Maybe not in full detail, but just to recap a little bit. So there are a couple of topics. One is graph representations, which we have been doing for a while. Graph representations are just different ways to store the graph. So the most initial way that we all learn to store a graph is adjacency matrix, which is just if you have n vertices, you store it n by n, and each entry is like the adjacency information for that edge UV, for example. And then this is an incidence matrix. It's like rather than the vertices on the columns, this is edges, and then you have like the edges, the vertices of the edges are connecting. So you don't usually use this for normal graphs, but you could use this for hypergraphs, which is like if you have more than 2 vertices per edge, then adjacency list is like you store n lists and each of them is adjacency. You're probably very familiar with this because you did the programming side. And then CSR, which is an array-based representation. Basically, you concatenate all the adjacency lists together And you keep a separate array, which gives you pointers to this thing. And yeah, so that is graph representations. And then we can just do one example of graph algorithms. So we will mostly be focusing on, if there are graph algorithms, there will be dense algorithms. The sparse algorithms are much harder. So dense algorithms is just, we're just going to assume that we store that in adjacency matrix form. And yeah, so the algorithms are spanning tree. These are basic algorithms, Prim's algorithm or Dijkstra's algorithm, or all pair short spans, which you could just do by running Dijkstra's n times. But in the slides, we do a bunch of ways to do EPSP as well. Yeah, so this is just how do I want to do this? Okay, so we can just do one of these algorithms. So let's just talk about Prim's algorithm for a minute. So Prim's algorithm is this greedy algorithm that basically works by you pick an arbitrary vertex, and then you grow your MST by selecting whichever one is closest to that vertex. And then you add that vertex into the MST along with the edge. And now you have like some MST with 2 vertices. And you keep going. So now the next step is you look at the rest of the vertices and you see which one is closer to the 2 vertices now that you have closest to either of the 2 vertices now that you have in your MST, and you add that one in, and now your MST is 3 vertices, and you keep going. So when we do the parallelization, it is hard to parallelize over. So the outer loop is going over, like you add one vertex into the MST at that time, and that is hard to parallelize. So instead, we're going to parallelize the part where you look. You have to find the main step. The inner loop is like you find the min over everything outside your MST to your current MST, and you add that in. So that part you can parallelize. So this is just the serial execution, like this is the graph in adjacency form, and then this is the distances, which is the current test. This is the serial pseudocode. So for all the outer loops like this, for all vertices that are not currently in the MST, you set the distance equal to, if the edge, well, first R is the start, which is an arbitrary start vertex. And then in the initial step, you just set, if any vertex is connected to V, which is your starting vertex, you add that to your distance vector. Otherwise, the distance is infinity, which is currently your MST just contains vertex R. And then while you still have things that are not in your MST, you basically just go over everything outside and you find the min. And then you add in this vertex U such that the U is this min of the distance over everything currently not in your MST. Good so far? Yeah, so the way that you do this in parallel, so the outer loop is serialized because it's hard. This kind of physical dependency there, but we can parallelize this part where we're gonna parallelize this part, which is finding the min, and then you're gonna parallelize this part also, which is finding the min for everything remaining. You have to update the distance vector. Yeah, and this is how you imagine doing parallelization, like each one of these block columns is separate data parallelization. And then, so this is the analysis. So there are n outer loop iterations. Each iteration, it has computation time n over p plus log p. Well, first, the initial step is to do this reduction to find the smallest element outside of your MST. And then the next step is that you have to do this broadcast, because once you select a node that goes into your MST, all other processors have to know about that. So this is broadcast. You have to update the distance vector. This can be done in parallel, also in n over p. And then the total time is just, you add these all up and you multiply by n, which is the total number of outer loop iterations you have. So the computation time was dominated by n over p plus log p. This is just that thing times n. So n squared over p plus n times log p. And then communication time was dominated by this broadcast. This broadcast is reduced, which is tau plus mu times log p. And that is communication time here, displaying times n. And then this last step is sufficient up to n over log n processors, and the way that you figure that is you try to find the setting of p that equalizes these in an asymptotic sense. Because efficient means like the communication is dominated by the computation.
So when you do that, do you just ignore the tau plus mu part?
Yeah, you kind of ignore the tau plus mu part, because, yeah, then you kind of try to set. And also you kind of figure that, well, depending on your setting of p, you kind of try to equalize these, or not necessarily equalize these two, but like, you have to be careful, you can't drop either one of these, because depending on the setting of p, this one might be bigger, this one might be bigger. So you kind of compare this whole thing to that one. Well, here, there's n log p on both sides, so.
I think I'm just forgetting about the reduce or where's the log p factor?
Oh, for the reduce, the way that you do the reduce is you have a vector of length n, and first you do local reduction on every cluster, so everybody has an n over p piece. So you do local reduce, which is n over p, and then you have log p, which is like the tree on p processors, and then it's like order notation, so once you do this tree reduction, so you do the tree reduction for one element per processor, which is the log p, and then once you do that tree reduce, you kind of like need to propagate that to your local sum as well.
Oh,
So that's another n over p, but since it's big O, it just goes away at the big O.
So like with other algorithms, like basically you can partition a matrix in like different ways and it will reach the same result. Is it the same for this algorithm, or does it have to be block column partitions?
Should the matrix is that way. I think you would not get the same row times if you partition the matrix in a different way. Like you can do it. You can partition it in a different way. But so for example, let's say we have like row wise blocking rather than column wise blocking. And the main operation that we need to do is that for all vertices, we need like. So the outer step is just, let's just consider the first step, which is you start with some vertex and you need to find the distance from vertex. Yeah, okay, so you need to find the distance from vertex V, which is, or vertex R, which is where you started, to vertex V, which is everywhere outside, everything that's not R. And so if it's with row wise, so you need to look at so every row is like the adjacency information for some vertex. And basically that's kind of like a lookup for position R in each one of those vectors, or each one of those rows. And so you could do that. So that's one column. And then you can do that in parallel because you have block rows, but now you need to update the distance vector. And so it depends on the partitioning of the distance vector as well. In that one, yeah, it's one column, so you can parallel that, but then everybody needs to update the upper and the distance vector. And then in the remaining part, you look at the outer. Yeah, so this part you find the vertex view by just looking at the distance vector, so you take them in, and you need to be able to take them in parallel. So the distance vector needs to be blocked like column-wise because it's only one row. And then if you can take them in parallel, that is fine. And then this one here, for all the vertices, yeah, for all the vertices not in the MSD, you need to take them in compared to the distance vector of that weight. V is varying in view space. So it's one row and different columns in that one row. So that's why it's column partition, because you need to be parallel to the column. But this part would be serialized with those row partition.
And also like if like these kinds of graph algorithms appear on the exam, like what format would it be more like? Would it like are we applying it or?
Isn't it, we're doing it might be something like thinking about basic algorithm such as this, like for instance, like I would give you the pseudocode and you'd be like, okay, how long does this step take, like this initial setup step? Assuming that it's complementary, for example, like how long would this setup step take to set the weight? So like how long would this front test, or how long would the mid step take, or how long would the front test step take?
So runtime analysis.
Yes. You don't have to come up with this paradigm. Is that okay? On that one? Do you want to keep going? Do you want to do something else?
Just wanna ask, do you have practice on graph algorithms available yet? Cause I'm not sure if I saw them.
Whatever I have is posted in the practice summer questions. Actually, these slides, well, not include the slides, but there's a book, I think it's this book, these books. This introduction to parallel computing. There's a section, this is from this chapter that they had on graph algorithms, so they might have some problems in there.
Okay.
Actually, I haven't looked, I just looked at the actual textbook part, not the questions, but
And also, is there any like, CIO's kind of incentive that we might be looking at for final or anything? Or, right now, we don't have any kind of curve so far.
there will be a curve at the end, but I can only determine it after the final, because I have to look at the total grade, the entire, like, holistically of the entire thing. There's no CIO certificate, though I recommend that you, I don't know, fill it out. I don't know, I see there's no, I don't, since there's a curve at the end, I don't really see any point in giving an incentive, because like, if one person does it, then everybody should do it, and then everybody's grade would be bumped up the same amount, which is the same under the curve, so that's why I didn't really see any reason, but, this is my first time teaching this course, so I would be happy to hear any feedback as well. And yeah, so for the gem, like, so regarding the curve, as I said, like, I can't figure it out until I see the finals, until I see the final section, but it will be, there are two sections in this course, like the undergrad and the grad section, so those will be considered separately. And what else is there? Yeah, so the curve, I will also look at, so like, I will try everything that I can to see if I can like give some reasoning to like bump up your grade. Like, for example, if your first two midterms weren't that good, but if your final is really good, then I'm like, okay, like maybe there's an upward trajectory. So like if you're kind of close to the cutoff, then I can try to push that. Or I can consider like the average grade or average exam grade, for example, versus like, oh, if you just had one really bad one, or if your programming assignments are really good, I'll be like, okay, like maybe you weren't so good at the theory part, but the programming part was really good. So yeah. It's not really fungible, but. For one data, I only have one data point, which is last year their curve was somewhere around the 6-ish, wasn't it? But like, it's not really comparable, it's like, I restructured a bit of the things and they had 200 students, so it's a bit harder to compare.
Gotcha.
Outside of the practice question, no answer, there's no practice exam, no additional practice material specifically for the final.
No, the majority is just from midterm 1 and 2, so you could redo. Or if you have already done them, or you could do them like there's several practice exams for both midterm 1 and 2.
Okay.
Yes.
As far as the algorithms go, like the sorting algorithms, prefix sums and FFTs, should we be more concerned about the implementation of these algorithms or application of these algorithms?
Most of the applications of those algorithms. So for prefix sums, like, I won't ask you to rederive like the bounds for prefix sum, it would be like, it would be like in the prefix exam, like, use prefix sum in some problem to solve it, or yeah, for FFTs as well, like in the homework, it's just like use FFTs to solve this other problem that is kind of related.
I don't know if you, so one of the FFT problems was on homework. I just couldn't understand that one. I don't know if you could go over one.
Yeah. Homeworks. Sorry, let me make it bigger.
First one.
Maybe I can also pull up the solution and see if that solves your issue. I don't know if you've already seen it.
No. Yeah, I don't want to waste time.
No, this is good. But at least we can look at it and see if there are anything else. If there's anything else. So, okay, so to recap, this question is, you have two vectors, a0 up to an minus 1, b, which is b0 up to bn minus 1, and you want to compute this output vector c, c0 up to c minus 1, where it's defined as this. So c sub 1 is the sum of j up to I. So I is ranging 0 up to n minus 1. And this is j up to I. Basically, you can see this as like A is going up and B is going down. And then this one is the remainder. So like I plus 1 up to n minus 1, which is the rest. And this is like this is the same, like A is going up and B is going down. Like I is fixed and J is the thing that is changing. So n plus I is fixed and J is increasing. So this index on B is going down. And so, yeah, and then, so what you have to do here, so for the FFT, if you have two vectors, if you have two n by n vectors and you see them as a polynomial, it doesn't immediately work. Like not every entry is one answer to this, because you need n outputs. C0 up to n minus 1, but the FFT will give you 2n of them. So how are we going to figure that out? Well, here says that the natural thing to do with FFT is you take the coefficients and then you treat them like polynomials. And if you solve this polynomial multiplication, then you have these coefficients. Like I said, you get like 2n minus 1 of them. You get about 2n of them, which is not directly correct because you need n coefficients for c. But this is just saying that that is these two things. Like you pair them off like I and n plus I.
I didn't see.
I think we posted a video about it on it. Briefly went around.
Over the question about the mesh in chapter.
Yeah. Question about the mesh. Maybe I have to remember it, but okay. Um, This one? This one. This one?
One before the
Oh.
second.
This one. Hold on. There's an updated version of this. Give me a second. I know there's a version with the answer in it. Yeah. Okay, this one. So suppose that a p-processor ring can be embedded into the p-processor array such that each pair of neighboring processes in the ring with corresponding processors in the array are connected by no more than 2 links. You have to write this mapping function. So often this one is so array is just like an array. is just the same as the ring, but without this end connection. And so it's saying, we have this thing, and we want to embed it into this thing. And so clearly the main difference is that this four, in the ring, 4 and 1 are connected, 1 and 4, but in the array, 1 and 4 are not connected. So they need to become, as it says in the problem, at most distance 2 from each other. So this mapping is just saying, like, you can kind of think of this mapping as you take the array and then you kind of like fold it on itself, such that the end is now next to the first thing, and then like the second to the end is next to the second thing, because these two, like 1 and 2, need to still remain distance 2 from each other, at most distance 2. So like in this example, it would be like 1, 4, 2. Because now 1 and 4, like 1 and 2 were distance 2, but now 1 and 2 are distance 2 from each other, and then 4 and 3, they were next to each other, but now 4 and 3 are distance 2 from each other. Yeah, 4 and 2 became closer, that's fine. Yeah, so does this construction make sense? And that's just what it says here. In more formal language. And then the questions are, give the values for the embedding performance metrics, load, expansion, congestion, dilation. So load is like how many vertices from the source mapping going to the destination. How many vertices from the source mapping get mapped to each vertex on the destination mapping, and you take the max over those. So in some embeddings, like 2 vertices might become 1 vertex, for example. And then, so that would be load 2, but here it's just a 1-to-1 mapping, you don't get any more vertices. Like, it comes of this thing. So this has the same number of vertices as that, so the load is 1. And the expansion is like in the other direction, which is sometimes the destination may have more vertices than the source, but here again, it's just only 1, so same. So load and expansion are both 1. And then congestion and dilation. So congestion is if you have, so for one edge in the source topology, how many edges overlapping may be in the destination topology. So here, for example, there is no congestion in the original implementation between 1 and 2, 2 and 3, 3 and 4. But here there is no congestion between these things because now so previously 3 to 2 and 3 to 4 had no conflicts with each other. But now 3 to 2 and 3 to 4 are overlapping in this edge. So that's why the congestion is 2, because now like 3 to 2 or 3 to 4 will be like this, and then 2 to 4 is like this, and they overlap here. So now you have some. If previously, like if 3 was transitioned to 4 and 3 was transitioned to 2, it do both of those independently, but now it's not in this estimation. So that's why that's why the congestion is 2. And then dilation is for every edge in the initial one, how many edges does it become? Like how does the distance increase in the estimation? So here 3 to 4 was 1 before, but then now here 3 to 4 becomes 2. 4 to 2 and 2 to 3. So that's why the dilation is 2. So I think I'll go with the information one. I know it was a long time ago, but to you is here.
Maybe this is more of a personal question, but I guess I'll ask for everyone. So our allocated 1-page sheet, do you have all of ours from exam 1 and exam 2?
Yeah.
Okay. If we're interested in picking that up, should I just contact you individually?
Yeah.
Okay. Save myself some extra writing.
Sure. But won't you have to write it again?
well, I can look at everything and then I can reduce from there.
I see.
rather than-
If you know, you just need like a photo of it, so you don't have to. Or you can, you know.
Oh,
You'll go for the cash.
Yes. Okay, well. So. So this caching, the pseudocode for Strauss's algorithm was given earlier, and we can look at it again, but just to remember, right now, like, at a high level, how this is working. So for caching, we're just always going to consider serial implementations, because it's hard to consider both parallelism and caching at the same time. And the main parameters, the main point of caching is that we introduce these parameters, which are the cache size M and the cache line size B. So in a cache of size M, we have M over B cache lines in it. And basically the way the caching works is that when you bring in one element, you actually bring in the cache line of B along with it. So you get B elements actually rather than one. And in the caching models, one cache line move is unit cost. So it costs you order one time to bring in order B elements. Yeah, and usually we do this in divide and conquer way. Oh, yeah. And so we don't even need to go back over the code, but basically the point of Strawson's algorithm is that in regular matrix multiply, you have 8 subproblems. You have 8-way recursion, and then you combine them into your quadrants. And in Strawson's algorithm, they figured out that you could do 7-way recursion, and then still combine them with some matrix addition and subtraction into the correct quadrants that you need. So this thing. So up there is the normal way that you would do it with 8 multiplications. You can see there's 8 submatrix multiplications, and then you combine them with addition. And then in Strawson's algorithm, there are 7 submatrix multiplications, and you combine them in a weirder way. But the additions and subtractions go away in the big O because they're not recursive. So the only thing that we really care about here is the number of multiplications, which is what is going to give us the recursion. This recurrence. So a little bigger. Okay, so yeah, so the recurrence is pretty much how all the caching recurrences look. There's 2 cases. One is the base case, which is if your size n is between 0 and some constant of root n, because here n is one side length, so your matrix is actually n by n. And so if you square that thing, that would become like some constant squared times n, where n is the memory size. And then yeah, so this top part is if your problem can fit into the cache, it costs n squared over b to bring in the submatrix. Submatrix you into the cache. And then once you bring them in, you may keep the actual algorithm may keep recursing, but you don't need to count it anymore because you're only counting cache misses for cache analysis. And there are no further cache misses because the problem already fit into cache. The second part is the recursive piece. So there are 7 submatrix multiplies. Each of them, the side length is halved on each side, so that's n over 2. And then this plus n squared over b is you can get to do matrix addition and subtraction to combine the products. Remember how to do this? Okay, so first question was, why is it like this? Why is this recursive case the way that it is for sufficiently large n?
It matches the recursiveness of the algorithm itself because it's calling it's recursive calls grass like 7 times for the 7 multiplications. Then, once you actually get to the, plus theta and square root of b, because like you're also doing like matrix addition and subtraction, so the storage of those matrices would require that much storage. approximately.
Exactly, so, there are 7 subproblems, so you recur 7 times. Each one has, the side length is halved, it's when you're in square matrices, the side length is halved in both dimensions, and this plus n squared over b is to combine the submatrices. And then second one is the base case, which is why is this n squared over b for n less than c root m. And that is because in this case, the problem now fit into the cache, so we don't need to incur. The main thing to remember is that in this model, we're only counting cache misses. You can, like, so there's some trade-off between the abstraction of the model and how useful it is. Like, this model is really easy to use, but in this model, like, if you have, it costs you nothing to do infinite work on what is already in your cache, which is also obviously unrealistic. So, you have to. But if you wanted to make it more fine-grained, then it'd be harder to use because then you would count other factors. So there's some trade-off there. But anyway, so here, y is q of n equals to this thing for n less than some small constant times root m, and that is because they just said if you square this, which is the actual matrix size, you square this n squared, and then it fits in the cache, so it just costs you this to bring in this matrix into your cache and then solve the entire subproblem from there. Okay. So sketch the recursion tree. Give the height and the number of leaves. Okay. So we start with q of n. And then we have 7, and then each of these is like q and over 2. Which is the height, this is the height of the total recursion tree of the entire algorithm. Yes,
Why is one theta 1 and not theta n squared?
I'm just writing the entire recursion tree of the entire algorithm. One way to do it is also to cut it off at n squared over b. But then, so the way that I find it easier to do is that you compute the height over this, and then you compute the height over, and then you compute the height when it gets cut off in some sense.
Oh, okay.
Does that make sense? So like this is the actual function itself, but then because when you do cache analysis, like it's just an analysis thing, you don't actually stop the recursion once you reach the cache boundary. So the height of this is log base 2. Yeah, so you cut it in half over time. This is log base, no, log base 2. No. Oh, yeah, because it's 7 branches. So the height is 1 n. And then the height, when you cut this off, is theta n squared over b, which is theta m over b. So then basically the way you do this is the height of the analysis is height is log n minus log m over b. And then the base case size is theta m over b. And then basically the way you do this is you want to count up all the work in the leaves. And then you're going to do that by the fan out is 7 raised to the height, which is the number of leaves that you have. This height times like theta m over b. And that's the total amount of cache misses that we're going to enter the entire thing. And then 7 raised to the height is just this. Sure. Yes, so this is the way that the analysis goes. You calculate the height, you calculate the number of leaves, which is this 7 raised to the height. In general, it's fan out raised to the height, but here the fan out is 7. The number of leaves is this thing, the misses per leaf is this thing, and Q of n is just by these two.
It's long from base 7, right?
No,
Or
the height is
factor?
log base two.
Is-
The fan out is 7, because the height is log base 2 because every time n gets cut to half.
So you have to leave the 7, otherwise then you have long base 7. Make 30 factor up to H.
Yes, but it would only be log base 7 if the problem got cut by 7. But the problem is cut by 2 each time. So this is like 7 raised to log n minus. No.
So you have to leave. Can't take the factor.
Yeah, I use that factor because. Like if it was 8, then it was nicer in the other way when it was 8.
Yeah.
You could swap the logs, I guess, like. You know, like, say, and
Yeah.
you can swap, like,
I'm a little confused over the part where you said, big O of n square over b is the same as big O of n over b. I'm confused why.
yes, so. Good point. So if we look back at the piece, this was n squared over b. And then this base case was q of n is theta of n squared over b for n less than this thing. So I just plugged in this thing into here. And that becomes m over b. Theta m over b. So, I guess going back to this log interchange for a second, like, yeah, you could make this like 2 to the power or something. Make this 2 to the power 1 base 7. Yes.
Also, I have one question there. So instead of using m over b, could we use that because isn't it at the same point as q of n over root b? Because like that's the point where we reach the recursion. But it actually equals that, so we can also do minus log n over root b.
Why would it be minus log? So you're saying like rather, so here this is log n minus log m over b, which is.
Yeah,
Is the height of the recursion until you hit the recursive, until you hit the caching base case.
yeah. I'm
Um,
saying is the caching base case at q of n over root b. Or because that's the same, or it sounds the same as n squared root b. No.
No, the caching base case is at q of. F, basically,
Q, okay.
where m is the caching size. Or m over b, I guess.
Oh,
Yeah, that's why like, you can kind of think of this in 2 parts, but the total height is log n. But the height, this is kind of asking like, what is the remaining height that you have to go after this thing is hitting m over b. Because at that point you start counting detachments, so this is log m over b. And then this, the whole thing was log n, so you want to count the number of leaves like here. So that's why it's log n minus 1.
Something like, interconnects, what were the examples?
Goodness. If there's a bit complicated, probably if there is one, it will just be similar to this, which is about omega networks. So because these are like you have to do some more thinking about like the independent network, but what we did in class was the omega network, which is like the flattened version of hypercube. And here you just have to write route implementation through the Omega network using, using like the shuffle algorithm. So. What I'll be like, if there's one.
Sorry, do you shuffle algorithms?
Let's do this line. So. Okay, so. If you remember this kind of technique, which is, we want to build hypercubes, but in reality, it's hard to build hypercubes because we need to build whatever it is in 3D space. And like with hypercubes, if you go into higher dimensions, then you have, then you'll have a lot of wires of different length and also wires that may cross each other. So we cannot, it's hard to build true hypercubes. So instead, something that is way easier to build is like kind of like flattened version of hypercube. So this is a butterfly where every node, the nice thing about these flattened version is that every node has a constant number of ports, which is something that we actually need when we have hardware, because the hardware number of ports is not arbitrarily growing with the dimensionality that we want. And the way this works is that, like, rather, so a hypercube has P processors, but instead we can simulate it with the flattened version with P log P processors, where every layer has P, but you have log P layers, and each layer, the meaning of each layer is like, the hypercube, these are like distance 4 from each other. And then this is distance 2, and then this is distance 1 from each other. So that would be corresponding to changing like which bit you flip in the hypercube. Because every neighbor of you is only flipped by 1 bit. So that's just that. Yeah, and then with this interconnect, you have 2 options. You have 2 inputs and 2 outputs, and you can either pass through the input on the same wire, or you can do the split where this input is going out to that wire and this input is going to that wire. And our goal is that we want to route hypercubic communication. And so instead, we're going to build this other network called the Omega network, which is generated according to the script of shuffle. So if we have here, we have 8 processors. And the way that we do these connections is you cut them up into left and right half. So if you imagine kind of like the deck of cards and you have 0 up to 8, you cut this in half. The left half is 0 up to 3. The right half is 4 up to 7. And then you just do like, you take 1 from the left and 1 from the right. So that's what I'm saying. That's what I mean by perfect shuffle. So like you take 0, and then you take 4, which is the top thing, the first thing from the right half. And then you take 1, which is the second thing from the left half. You take 5, which is the second thing from the right half. And then so on. So that would give you another sequence of 8 numbers. And we do the same thing, which is you cut it in half, again, left and right half, and then you redo the shuffle here. And then if you redo it again, you will note that we get back to where we started, which is 0 up to 7 in order. And then, so that is, yeah. And then the connections between the levels are just the same number, yes.
Is it the same thing as like writing the bits out and flipping them?
Yes, yeah, so this one is, like 0 and 4 are you flip the top bit, and then 1 and 5 are you flip the top bit. And 2 and 6 and 3 and 7 as well. And then here, 0 and 2 you flip the second bit, and 4 and 6 you flip the second bit, and 1 and 3 and 5 and 7. So that's exactly. And then the connections across the levels are just the same numbers. So like 0 is always connected to 0, and that doesn't move. 1 is connected to 1, 1, 1. And yeah, so this is just back where we started again. 1, 0, 1, 3, 7. And so to route things through this network. Yeah, it's just P log P. Okay. And then to route things through the network. One cool thing is that you don't need to look at any information about the source. you just need to route it in an online fashion according to the bits in your destination. So, for example, let's say we want to route from 010 to 101. So we start at 0, like we need to know where the source is, but in the routing, we don't look at the source. So we start with 010, and that is connected here. And the algorithm is, so every box has 2 wires outgoing. And if the bit is 0, then we route through the upper output. If the bit is 1, then you route through the lower output. So 101, first we look at 1. So we route through the lower output, we see 0, the second bit here. We route to the upper output there, and then we see 1, we go out here, and this is 101. And the point of this is that this will, given any hypercubic permutation, you can route through this thing with no convention. And the reasoning for that is in hypercubic permutations, only 1 bit flips. So, yeah, and so you'll never get convention on any of the output wires.
If you go to the previous without the connection.
Sorry, you have a question?
Yeah, this is like, what do you mean by arbitrary permutations?
Oh, I just mean, if you have log n bits, you can flip any one of them in every. To get any hypercubic permutation, you just have to, you pick 1 bit to flip, and everybody flips their bit, and they're trying to go from the input to the output. And then you can, so for every processor, let's say you just flip the top bit, you can route a permutation that would send from any processor to its neighbor with the top bit flipped, or the second line of their one, so.
I don't really understand how the two, like how the table is related to the diagram. Like, for example, what does it mean by 1, 5, 30?
So you can think of, okay, so we start with the number 0 through 7. And to generate the next level, the next layer in this network, we cut 6 in half and here. So now we have left half, which is 0, 1, 2, 3, and right half, which is 4, 5, 6, 7. And then we want to, the way that we're going to create the next level is to do this shuffle, which is you take you take 1 element from the left and 1 element from the right, and then 1 element from the left and 1 element from the right. So 1 element from the left is 0, 1 element from the right is 4, then 1 element from the left is 1, and then 1 element from the right is 5, and so on. And then so that's just what we got here. We took 1 from the left and 1 from the right. And now the thing to notice is by construction, these, you can think of these as like pairs, like 0 and 4, 1 and 5, because those are like 1 from the left and 1 from the right that we got. And each of these pairs is the same, except the top bit is split in the bottom. And then if you do the same strategy again, now you cut the left and the right again. So here left is 0, the right starts at 2. So now we have 0, 2, 4, 6, and 1 from the left, 1 from the right. And now now the pairs are the same, but you have flipped the second bit. And then if you just redo the shuffle again, then this is just the initial order. And this diagram is just how you construct this, like what is the left and what is the right. So you cannot route arbitrary permutations through this. Or you can route any permutation you want, but it may not be efficient. But some of them may not be hypercubic, but they may still be efficient. So, yeah.
What was the example where you can't route?
So let's just looking at 2 messages. If you're trying to route 010 to 111, and here we're trying to route 110 to 100. These are the routing paths through this. And we get these two both want to go out this way. We started here and here. Both of them come to this box and both of them want to go out. Both of them want to go out on the bottom wire. They come out here on different wires, but there will be some connection to come out this way.
So is there like a mathematical formalization about like when congestion would happen?
So if you look at this routing algorithm. I don't know of a full. Like a full theorem about it, but maybe we can see some cases where it would, which is like, if two things are going into the same box, if they share the same bit. Like, it just happens when two things are in the same box and then they need to go out the same wire, which is if they have the same bit in that position. So. Here, and things come to the same box when, like in the first, let's just look at the first level. Things will come to the same box in the first level if they have the same lower bits, but just here like 0, 1, 0 and 1, 1, 0. Those are the same except the top bit is flipped, so that's why they would go into the same box and layout.
What would the congestion of the Omega network be?
The congestion could be at maybe at most 2, because in each wire or in each box there are at most 2 inputs. And then, so then there can also be at most 2 outputs, but maybe. Congestion compound. Like in every single box, in each individual box, that congestion can only be 2 going out. But. Maybe it could be 2 times lucky, because they're lucky levels, and then each one, like, or, actually, I'm not really sure about this, but maybe. Like 2 can go out here, but then 2 can also go out here, and then now you have 4 in this box. And then. Oh, but then. Would it be 2 raised 4? Then would it be P? Because then like if you got 4 out here, then would it be like 4 out here too? And then you have like P levels and each one is increasing by power of 2. I'm not sure, let me get back to you on that one.
Do most modern architecture use the Omega network or is some variant of it?
It's a good question. Networks are very varied. You can actually look, I think, at. Never mind. I was trying to look for like, there's a list of the top 100 supercomputers. And then I thought that there at some point was some correspondence with that list and what interconnects they use. I think they probably need like the bigger ones probably use something very fancy, like. There's like randomized routing schemes for example, stuff that is more complicated, but. I think more simple ones might be something like this.
So what exactly he does is talking about implemented. What kind of question?
Oh, just like the. Here, this is an example, which is like you draw the interconnect and then you route some permutation through it. And you can see like if there's some conflicts or not. And then these are also. These are not related to Omega networks, these are just related to other interconnects. I don't know, these are mostly just about like routing and hypercubes, so. I don't think. I don't really go through these. Yeah. But they might help you to understand the rest of it, so I posted the solutions online.
Will there be any problems in the in-body? Oh, I noticed in the homework, there were only problems in the quad tree or hot tree. Will there be anything more than that?
Probably not. Like maybe some like true false question or something about like the structure of the embody, but nothing really about like re-deriving any part of the actual embody algorithm. That was mostly just because like I thought it was cool. If there are no questions, I don't want to keep you for too long, so, yeah. I will see you Friday. Yeah, thank you.
What are the office hours this week?
There will be some Friday, but there will not be Wednesday, Tuesday.